Hello, this short demonstration continues on the previous tutorial on how to complete the rocket science sample game. This game is about the rocket flying from the Earth to the Moon, but the version that you received as the starting point for development has all the graphics in place but no mechanics, so the only thing I can do with the rocket is to rotate it left or right, but I cannot fly. So we have been previously working with this canvas-based development recipe, and here we have 10 steps to succeed. In the previous tutorial that you should definitely watch before this one, and you can find this previous tutorial here down the page in Canvas. So in that previous tutorial we have started the project and we have gone through the first 2 steps to succeed. So I will now go back to the compiler, rearrange the screen so that I have my source code on the left and the steps to succeed on the right. And just a quick reminder, step number 1 was already built, was already implemented in the starting version you receive, and step number 2 was about calculation of the mass of the rocket. This mass is stored in a variable called, surprise, mass of the type float, and according to the step 2, this should be the total of the own mass of the rocket and the fuel. But scrolling down you can notice that the fuel can be found through the useful function getFuel, and we indeed are using this function here, and the rocket own mass is shown here. The rocket own mass, empty mass, not counting the fuel, is 120. So the calculation is 120, the rocket mass plus getFuel, the fuel mass. This provides the total mass. Now, step number 3. Calculate the distance from the center of the Earth to the rocket. Find the x-coordinate of the planet and your vehicle. I will show you our game once again. The rocket is here, and we can find its x position and similarly y position using the corresponding functions in GFC. So is that it? Yeah, get x retrieves the x coordinate of the sprite. So this is how we are going to find the x coordinate of the sprite. Now the distance between the rocket and the Earth is in fact the distance between the center of the rocket, which is easy, and the center of the Earth. The center of the Earth will be probably somewhere outside the screen, somewhere here. So the distance we are looking for is something like this. Similarly, in the next step, in the step number 4, we will calculate the distance between the rocket and the moon. So we will need the position of the center of the moon, which is actually somewhere to the right from the window. Can we find any useful information here? Of course we can. Game engine values show the position of the Earth center. It's -100. Why -100? Because it's to the left from the edge of the window. The edge of the window is 0. Everything to the left from there would be a negative number. And I will just spot the position of the moon center. Should be of the moon, not if the moon. 900. It is to the right of the edge of the window. Edge of the window coordinate is 800. The center of the moon is 900. Okay, scroll back to our steps and let's try to do the actual calculation. It's already started, so we have a definition of a variable. I just need to uncomment it. Okay, and now what is the Earth distance? Earth rocket. The rocket is on the right, so if I take the rocket x position, which will be just get x. Okay, Visual Studio even gives me a hint that this is this. Okay, This is a function, so I need a pair of brackets, even if in this case this pair of brackets is empty, and this is minus negative 100. Okay, I have minus here, double minus, so I can replace it by a single plus. So it's get x plus 100. Step number 4, calculate the distance moon rocket. Again, I will uncomment the definition of the variable. Now the moon is more to the right than the rocket, so I start with the x-coordinate of the moon, which is 900 minus get x. Okay, in fact it doesn't matter whether you put here 900 minus get x or get x minus 900. I will show you why in the very next step. The very next step is calculation of the gravitational force between the Earth and the rocket, and then the rocket and the moon. So we have two different forces here. So I will start with a similar step as we did previously. So it will be a float value. I will call it a gravity from the Earth. Okay, equals. What does it equal? Number 5. You calculate Earth and Moon gravitational force using the famous Newton formula. It is here. You will need values of G and M, rather unlikely to be similar to the real physical values. Check the tables below, or even better, find your own value through the experiments. We will go the easy path, so I will just scroll down and find out that the GM value for Earth is 12,000. GM stands for the gravity constant times the mass. The big M is the mass of the planet in this case. By far GM is not General Motors in this example. So let's find out how to actually achieve the correct value here. That's the Newton's formula. Okay, and I will try to create some C++ code. So we call this variable G Earth, okay, and this is equal G times M. Remember we had General Motors GM value is in the table, and it's 12,000. It doesn't have to be calculated in any way, because please note that G is one of the fundamental constants of the universe, and M is the mass of the Earth. When I checked this for the last time, it doesn't change too often. Okay, so 12,000 represents GM. Next part is the small m. Okay, that's the mass of the rocket, so it will be times m. M is, no, we actually called it mass in our code. That's the variable that we have already calculated, the mass of the rocket. Now, division in C++ must look like this. R squared in case of the gravity of Earth is the variable which we have just calculated. Okay, that's this one, this one, R Earth. So I will divide it by R Earth. And now I have to square it because we are representing this part of the formula. R Earth squared. The fastest way of squaring in C++, not swearing but squaring, okay, finding the square of a number in C++ is by multiplying by the same number, okay. So this is the fastest. There are other methods like a power function, but this function is very powerful but not particularly fast. Now the problem is that if you write it like this, and this is a common mistake, this would in fact make a calculation like this: GMM divided by R multiplied by R, okay, multiplied by R. This is definitely not what we want to get, not this. Therefore we have to add a pair of brackets here in order for C++ to exactly understand what we are going to do. This leads to another form of the same instruction. We could also do it in this way, equals 12,000 times mass divided by the distance from the Earth and divided by the same distance again. Okay, so instead of dividing by a product of this variable which requires additional pair of brackets, we can just divide it twice, and this will be, you know, divided by r is the same thing as divided by r squared. With this, I can now go back to our previous arrangement of the screen, and I am ready to put the code here. It was 12,000 times mass divided by r Earth divided once again by r Earth. You can of course Earth. Okay, you can of course use the notation with the multiplication and the bracket instead. It's absolutely up to you. Now I will use the programmer's best friend, copy and paste operation. Copy and paste in order to find the gravitational force from the moon. So what I need here is to change the G-Earth to G-Moon rather. Okay. Find out the GM value for the moon. It's 3,000. 3,000 times mass divided by, now I will need the distance to the moon, so it's r moon here and here. Done. Yeah, that's finishes step number 5. So we are now ready to proceed to step number 6. You also need the engine force, which is simple to find if you know the current setting of the thrust, but you may need an extra factor to make it more playable. Alright, so thrust, another variable, sorry, float. Thrust, I will just call it thrust. Alright, and what it could possibly be, we need to find the current setting of thrust. Is it in the useful function? Of course it is. Get thrust retrieves the current thrust level. Please note that get thrust is not a GFC standard function. It's a function introduced to our rocket class. The rocket class that looks like this, and I have gone through all these functions in the previous tutorial. Get thrust was just one of them. Okay, so we have get thrust, okay, and they say we may need a multiplier for this value, yeah, so extra factor to make it more playable. I will again go an easy path and find out the game engine values. A multiplier for the thrust value, recommended value, is 25. You would normally implement this model and find out that your rocket is either too fast or too slow, and in the trial and error process you would normally find the right value for this multiplier, but I'm showing now an easy way. That's the value I found previously, so why not use it. Step number 7, calculate the net force. When this exercise was given as an in-class exercise, this was the place where people made most mistakes. Why? Because this is actually getting together the three forces that we have already calculated. So the Earth gravitational force, the Moon gravitational force, and the thrust. So the general force equals, first of all, it's the thrust. Okay, that's the thrust of the rocket It's the main thing that works here. The second thing is the gravity of the Earth. We have to subtract this gravity, G Earth, because the gravity from the Earth tries to pull the rocket back, so it counteracts the thrust that we are generating from the rocket engines. And then we have the gravity of the Moon, which has to be added. Why? Because actually the Moon is also pulling the rocket, but the other way around. It's trying to attract the rocket to itself, so it's helping us in the journey to the Moon. Closer to the Moon, this help will be too strong, of course, and may easily cause crashing on the surface of the Moon, but that's another story. Alright, we have the net force, step number 7, just 3 more steps to go. Step number 8. Use Newton's second rule of motion to calculate the acceleration. I even have provided a formula for this. A equals F over m. Okay? So, float acceleration. One thing that I'm using in C++ coding, I rarely use, sometimes I do, but I rarely use the physical symbols. So in physics we tend to use single letters to symbolize all the stuff here. In programming I prefer more informative names, particularly that quite often in the code you might want to have something like a variable a, so acceleration will be the variable ACC, like acceleration. Acceleration equals F over m, so that's force divided by mass. Here it is, force divided by mass. Just a double check, we have calculated the force here, we've calculated the mass here, should work. Number 9, calculate and apply new speed. This is accelerated motion, and you know the acceleration. New speed is the speed so far plus gain of speed due to the acceleration. You may know that there are several different approaches to do this. I will follow the hint in the comment. Name of the rocket's functions you may need here. Get speed to obtain the current speed, and set speed to update the speed. So, set speed. Set speed to what? To the previous speed of this rocket, which I can get as the get speed. Get speed, empty pair of brackets, plus the portion of the acceleration that was created by or generated by our forces. So this is acceleration, but velocity in accelerated movement is v equals at, okay, acceleration plus time, and actually this is the delta time, so the increase of the time from the previous frame. This time that elapsed from the previous frame is actually provided in this function. If I just slightly scroll up, you can find the heading of this function. This function gets two values. Time is the current time, and this is nothing we would like to use now, but delta time is the time elapsed since the previous slide. So this delta time is exactly what I need to use in order to find the increase of the speed. Times delta time. Those of you who have semicolon to finish the C++ instruction, those of you who have some more experience with GFC perhaps might say, oh, why not use the accelerate function instead of set speed, get speed, and you are perfectly right. Okay, using the accelerate function is another way of achieving the same goal. In programming, quite often, if not always, there is more than one way to achieve a success. So obviously this is not the only form of the correct code. And we have arrived in this way to step 10, update the object possession. The comment says, I'm nice, did this part for you. That is how it should look like. Done! Alright, so the game should be working now. So let's try to build it. Can I fly? Oh, apparently yes. I crashed. So let's try to, alright, negative thrust. Okay, go to the moon, not back. Negative thrust. Oh, that was the very elegant landing on the moon with a final speed of 2. Yeah, so that's all, folks. That's how this rocket science could be successfully finished. The take-home message is coding physics. You should just follow physics. Alright, there are not particularly complicated procedures to convert physical formulas into C++ code, into C++ code like this one here, or like this one here. And the second big take-home message I would like to emphasize here is that there are quite often more than one way of doing the same thing. Like in this case here, both these instructions are perfectly correct and will be perfectly fine to work. Thank you very much for watching, and enjoy your own programming. I crashed to the earth. Thank you and goodbye.